Hi students, this is a third educational video among a series of tutorials showing how to analyze a loaded frame in terms of normal force, shear force, and bending moment diagrams. Of course, I'll explain this as simply and as clearly as possible. Okay, let's go. Well, first let's describe our problem. So we have a frame ABCD as it is depicted in this slide. This frame is constituted by left-hand and right-hand columns as vertical elements and a beam as horizontal element. The height of the frame is h equal to 4 meters and the span is s equal to 7 meters. The frame is supported by a pennant support at the bottom of the left-hand column at the point A and a roller support at the bottom of the right-hand column at the point D. The frame is loaded by a uniformly distributed load UDL equal to 5 kN per meter along a portion of the beam distant by 1 meter from the point B and 2 meters from the point C. And the left-hand column is loaded by a triangular distributed load with 0 kilonewton meter at the point A and 7 kilonewton per meter at the point B. The frame analysis consists in 5 steps. The first one is the determinacy checking. The second one is the determination of the reactions at the joints A, B, C, and D. The third step is the drawing of the normal forces diagram for the columns and the beam. The fourth step is the drawing of the shear force diagram for the columns and the beam. And the fifth step is the drawing of the bending moments diagram for the columns and the beam. Well, for the first step, determinacy checking, it's to note that the frame considered in this educational video is supported by a pennant support and a roller support exactly in the same way that the frame analyzed in the educational video frame analysis tutorial 1. So I invite you to see the link that I share in the box description. Now I'll explain how to determine the reactions at the point A and D. So at the point A we have two reactions, RAX and RAY, because we have a pivot support at the point A. And at the point D we have one single reaction denoted simply by RD because we have a roller support. The UDL can be simplified into a point load with a magnitude equal to the UDL multiplied by the length of the portion occupied by this UDL and applied at the mid-length of this portion. And the TDL, the triangular distributed load, can be simplified into a point load with a magnitude equal to the maximum value of the TDL multiplied by the half height and located at a distance equal to the height divided by 3 from the point B. Now, in order to determine these reactions, we have to apply first the equilibrium equation of moment at the point A. Why at the point A? This is because we have to neutralize RAX and RAY in order to determine RD. And if we apply this equilibrium equation of moment, we have finally RD equal to 13.9 kilonewton. Now, if we have to determine the reaction RAX, we have to apply the equilibrium equation of forces along X, and we obtain finally RAX equal to minus 14 kilonewton. So here RAX is negative, so it will be oriented towards minus X. And now finally we have to determine RAY. So we will apply the equilibrium equation of forces along Y, and finally we obtain RAY equal to 6.1 kilonewton. Now I'll explain how to determine the normal force diagram. So based on this free body diagram depicted now in this slide, if we examine the left-hand column, we have a vertical reaction equal to 6.1 kilonewton applied at the bottom of the left-hand column along the longitudinal direction of this column. In order to maintain equilibrium of this column, we have to add a 6.1 kilonewton applied at the top of this left-hand column and in the opposite direction. In the same way, we have to add a 30.9 kilonewton applied at the top of the right-hand column in order, of course, to maintain its equilibrium. Now, if we examine the force 6.1 kilonewton applied at the top of the left-hand column, this force will be transferred to the left-hand edge of the beam in the opposite direction as shear force. And in the right-hand edge of the beam, the shear force will be this 6.1 kilonewton minus the UDL, which will give finally 13.9 kilonewton or minus 13.9 kilonewton. Of course, here minus means that it is applied in the minus y direction. So based on this free body diagram, we will determine the normal force or the normal forces diagram. So for the left-hand column, we have a compression by 6.1 or 6.1 kilonewton. So we have minus 6.1 kilonewton applied along the left-hand column. In the same way, we have minus 13.9 kilonewton applied along the right-hand column. And if we examine the beam, we have no normal forces. We have no forces applied along the longitudinal direction of the beam. We have only transverse force, which are shear forces. So we have no normal force applied along the beam. We have 0 kilonewton normal forces along the beam. Now I'll explain how to determine the shear forces diagram. So based again on this free body diagram and also based on the fact that the shear force is equal to minus the integral of the applied force along the longitudinal direction of the member, denoted here by the letter N. So for the column, the longitudinal direction is y, and for the beam, the longitudinal direction is x. Based on all of this, we can determine the shear forces diagram. So now if we examine the left-hand column, we have an horizontal force applied as shear force at the bottom of the left-hand column. It's equal to 14 kilonewton. So we have a shear force equal to 14 kilonewton at the bottom of the left-hand column. Also, if we examine the triangular distributed load, we have 0 kilonewton at the bottom of the left-hand column, and we have 7 kilonewton per meter at the top of the left-hand column. So we can determine the expression of the TDL in function of y, which is the longitudinal direction of the left-hand column, and here TDL is equal to 1.75 y. In fact, if we verify this, for y equal to 0, we have a TDL equal to 0, and for y equal to 4 meters, which are the height of the left-hand column, we have the TDL equal to 1.75 multiplied by 4, which will give finally 7 kilonewton per meter. So we have now the expression of TDL in function of y. If we take also into consideration the fact that the shear force is equal to the minus or is equal to minus the integral of the applied force, which is here the TDL, along the longitudinal direction, which is here the y direction, we can obtain the expression of shear force in function of y as it is highlighted by the square, or as it is highlighted by the red square. And we can, based on this expression, we can determine the evolution of the shear force along the left-hand column. For the right-hand column, we can notice that we have only normal forces. We have no shear forces, so we will have 0 kilonewton as shear forces in or along the right-hand column. Now for the beam, we have 6.1 kilonewton as shear force applied at the left hand edge of the beam. So we have here this 6.1 kilonewton, which will remain constant along a distance of 1 meter. And at the right hand edge of the beam, we have a shear force equal to 13.9 kilonewton, and this shear force will remain constant along a distance of 2 meters. Now in the intermediate portion of the beam, we have a UDL equal to 5 kilonewton per meter, and since the shear force is equal to minus the integral of the applied force, which is here the UDL, along the longitudinal direction of the beam, which is here the direction X, we have an evolution of the shear force linearly decreased with a slope equal to minus 5 kilonewton per meter. And if we have to determine this distance X as it is depicted in this slide, the distance for which the shear force is equal to 0, we apply the linear equation of this evolution, and we can determine finally x equal to 1.22 meters. Now I'll explain how to determine the bending moments diagram. So based on the shear force diagram, we can determine the bending moment diagram, since we know that the bending moment is equal to the integral of the shear force along the longitudinal direction of the considered member. So for example here for the left hand column, since we know the expression of the shear force in function of y, we can determine the expression of the bending moment in function of y. And based on all of this, we can determine the evolution and the values of the bending moment along the left hand column. For the right hand column, we have a shear force equal to 0 kilonewton, so the bending moment can be 0 or constant. Or we know that the support at the bottom of the right hand column is a roller support, so the rotation is free. So at the bottom of the right hand column we have no bending moment, and based on all of this, we can deduce that this bending moment will continue to be 0 kilonewton meter along the right hand column. Now for the bending moment along the beam, the bending moment equal to 37.31 kilonewton meter applied at the top of the left hand column will be transferred to the left hand edge of the beam, and the 0 kilonewton meter applied along the right hand column will be transferred to the right hand edge of the beam. Now, based on this 6.1 kilonewton as shear force constant along 1 meter in the left hand side of the beam, we can deduce the bending moment as a linear increasing evolution with a slope equal to 6.1 kilonewton per meter. In the same way, based on this 13.9 kilonewton as shear force constant along 2 meters in the right hand side of the beam, we can deduce the bending moment as a linear decreasing evolution with a slope equal to minus 13.9 kilonewton per meter. Now, based on this area 1 of the constant shear force in the left hand side of the beam, we can determine the bending moment at the point distant by 1 meter from the left hand edge of the beam as 37.31 plus the area 1, which will give finally 43.41 kilonewton meter. And based on this area 2, we can determine the bending moment at the distance equal to 2.22 meters from the left hand edge of the beam. This bending moment will be 47.13 kilonewton meter as 43.41 kilonewton meter plus the area 2. And based on this area 3, we can determine the bending moment at a distance equal to 5 meters from the left hand edge of the beam, which is equal to the distance equal to 2 meters from the right hand edge of the beam, this bending moment will be 27.81 kilonewton meter as 47.31 minus the area 3, because we are in the negative side of the shear force diagram. Finally, based on the fact that the bending moment is the integral of the shear force, we can determine the shape of the bending moment evolution in the intermediate portion of this beam. This educational video takes end. If you have any questions, remarks, or suggestions, please do not hesitate to mention it in the comments. Thank you very much for your attention.